Hi everyone. Today we're talking about similar polygons today, chapter 6, lesson 2. We've talked a lot about congruent figures, especially congruent triangles. We proved triangles congruent through several different methods and stuff like that. Today we're talking about similar polygons. Now congruent is same size, same shape. Similar polygons, they have the same shape, but they're significantly or it could be significantly different sizes, such as these two hexagons up here. These hexagons are similar. You certainly wouldn't say that they're congruent. The purple hexagon is significantly larger than the yellow hexagon. However, they are similar. Maybe the purple one is just 3 times the size of the yellow one, or the yellow one is 1/3 the size, that kind of a thing. So that's what we're looking at today when we're talking about similar polygons. Please write this down in your notes. Similar polygons, here are the 2 aspects about similar polygons that you need to understand. The corresponding angles are congruent. So just like congruent triangles or congruent polygons, the corresponding angles are exactly the same. However, the corresponding sides are not congruent. The corresponding sides are proportional. So the relationship from one side to the other, they equal the same fraction. That ratio is the same. So the sides are proportional but not congruent. So let's take a look at these 2 trapezoids that we have up here. Basically, we're going to determine, are these 2 similar polygons or not? Well, are their corresponding angles congruent? Angle M corresponds to angle R, and they're both 120 degrees. And as you can see, J and U are both 45 degrees. K is 55, T is 55. And angle L over here is 140, and so is angle S. So are the corresponding angles congruent? We would say that the answer is yes, because the corresponding angles are congruent from one polygon to the other. Now we have to determine, are the corresponding sides proportional? So to do that, let's kind of break this down one step at a time. Write the ratio for each set of corresponding sides. So the ratio, MJ is the side that I'm going to start with. MJ. And that segment corresponds to what segment in the other polygon? Well, it corresponds to segment RU. And that makes sense, right? Like the side that's made up by the 120 degree angle and the 145 degree angle, its corresponding side is the 120 and the 45. So my next ratio that I'm going to write down here is JK. And what does segment JK correspond to? It corresponds to UT. And now I'm going to have LK as my third segment, and that segment corresponds to ST. And then the last one that I'm missing is ML. That segment corresponds to RS. Segment RS. So I have wrote the ratio for each set of corresponding sides. Now let's take a look at the relationship between those values. Replace the sides with the length of each side. So MJ is 12. So right here, I'm now going to write, instead of the segment, the value of that segment. So it's 12 divided by 3. 12 divided by 3. And JK divided by UT, JK is 26, UT is 6.5. 26 divided by 6.5. And then I have LK over ST, which is 17 over 4.25. And then my last ratio is 20 divided by 5. All right, so what do you notice about all of these fractions? If we simplify each of them, we could do this in our calculator. 12 divided by 3, you probably don't have to do that in your calculator. That number is 4, or 4 over 1. What's 26 divided by 6.5? That number is 4. What's 17 divided by 4.25? It is 4. And what is 20 divided by 5? 20 divided by 5 is 4. So as you can see, these are proportional side lengths. A proportion means that it's two fractions or two ratios that are equal to each other. And this fraction equals this fraction equals this fraction equals this fraction. So the side lengths are not congruent. One is smaller than the other. However, the side lengths are proportional. Their fractions equal each other. So if their side length or if their angles are congruent, and if their side lengths are proportional, we can now say that these two polygons are similar. So now we're going to write our similarity statement, and here it says order is important. On your first polygon, you could name this polygon starting at any vertex you want, and then you can go clockwise around or counterclockwise around. So I'm just going to start with angle M. So I'm going to say this quadrilateral, and here's how you label the quadrilateral, quadrilateral M. Now I could choose to go J, K, L, or if I wanted to go counterclockwise, I can go M, L, K, J. Just make sure you go around the figure. You can't name this polygon by going across the figure. You can't name it M, K, L, J, that kind of thing. So pick any vertex you want to, and then go around the figure either clockwise or counterclockwise. I will say quadrilateral M, J, K, L. So M, J, K, L. M, J, K, L. Now I said with the first one, it doesn't matter where you start, just pick one, M, J, K, L. Now on the next one, that's where the order is significantly important, because we're going to write is similar, and when we write that, this segment or this symbol right here, this means it's similar to. Now it's going to be similar to quadrilateral. Now if I started with angle M, I got to start with the angle that is congruent to angle M, which is angle R. So I have to start with angle R. That's why the order is important. And then if I say J second, then I have to say U second, because J and U are congruent. So U and then T and then S. So now this similarity statement is important to me, because just as I stated, now I can know that this angle is congruent to this angle. Oh, sorry. The K is congruent to the T because they both come third. The L is congruent to the S because they both come fourth. I can now say that segment MJ is proportional to segment RU. They're not the same length, but they do, the proportion is the same. JK and UT are corresponding side lengths. So that's why that similarity statement is so important to us. The order is very important. Okay, let's define what a scale factor is. A scale factor is a ratio of corresponding side lengths. We always write scale factor using the same units. In parentheses, you can write this too. Oftentimes, the scale factor is the number you multiply by. That scale factor is kind of the number that's saying how much bigger is one figure than the other. On our previous example, the scale factor was this number 4 right here. They all reduced to the number 4. So this figure right here is 4 times bigger than this one. As you can see, 20 is 4 times bigger than 5. So that length is 4 times as large. So the scale factor is the ratio of the corresponding side lengths. On our last example, it happened to be 4 to 1, or 4 times bigger. So let's look at this one. An architect prepared a 12-inch model of a skyscraper to look like a real 1,100-foot building. What is the scale factor of the model compared to the real building? So let's take a look. We have to write down the ratio because that's what a scale factor is, a ratio of corresponding side lengths. And it says of the scale factor of the model to the real building. So model is going to go in the numerator, and the real building is going to go in the denominator. That's the ratio of the corresponding side lengths. So the model is 12 inches, and the real skyscraper is 1,100. So I have to put them in the same units, so I have to put them both into inches or both into feet. It doesn't matter what you do. I would say let's put this one into feet, because 12 inches is 1 foot on the nose, isn't it? So the model is 1 foot, and the real building is 1,100. So there is our scale factor. The model is 1/1,000th the size of the real building, or the real building is 1,100 times the size of the model. So there's the scale factor for this one. Going to ask ourselves the question, are these triangles similar? Well, for them to be similar, two things have to happen. The corresponding angles have to be congruent, and the corresponding sides must be proportional. Well, if we look at these, are the corresponding angles congruent? The angle that is the vertex angle of this isosceles triangle is 50. So for it to be a similar polygon, the vertex angle has to be 50. Is it 50 on the next one? Absolutely not. These two are not similar. No. On this one, are these triangles similar? Well, their angles have to be congruent and their side lengths have to be proportional. So at first glance, it might look like they are not similar because their angles do not match up, or their angles are not congruent to their corresponding angles. However, it doesn't give us the measure of angle C, but I could find the measure of angle C because there's 180 degrees in a triangle. So 80 plus 60 is 140. So if I take 180 minus 140, I get 40 degrees. So this angle is 40. And I could find angle R by taking 80 plus 40 to get 120. And then 180 minus 120 gives us 60. So this angle is 60. So I ask you the question, are the corresponding angles congruent? Sure they are, right? 80, 60, and 40. 80, 60, and 40. We have congruent angles. Now we got to see if the side lengths are proportional. So I'll just start with 5.2. This 5.2, what does that correspond with in the other figure? It's the side that's made between the 80 and 60 degree angle. So the side that's made with the 80 and 60 degree angle is the 3.9. So 5.2 over 3.9. Now I'll go to AC. So what side does AC, what side does the 8 correspond to? Well, it's made with the 60 and the 40 degree angle. So the 60 and the 40 degree angle is the number 6. So 8 corresponds to 6. My last segment is 7. What does 7 correspond with in the other triangle? It is the last one. It's the 5.25. Well, class, if this is a similar triangle, then these all have to equal the same number. What is 5.2 divided by 3.9 in your calculator? It's 1.3 repeating, isn't it? What's 8 divided by 6? It's 1.3 repeating, isn't it? What's 7 divided by 5.25? It's 1.3 repeating. These are equal fractions. So if they're equal fractions, these side lengths are proportional, and this is a yes. Are the triangles similar? Yes. The corresponding angles are congruent. The corresponding side lengths are proportional. All right. Now let's use this to solve problems. We have a larger pentagon and we have a smaller pentagon. And this symbol right here is very important. It says that they are similar. So if they are similar, we could set up a proportion to solve for their side lengths. So if I just look at this one for a moment, I'm going to say what sides correspond to each other. The 6 right here is in between the 4 arcs and the 5 arc angles. And the 4 is in between the 4 arc and the 5 arc angles. The 8 corresponds to the y plus 1. And the x is in between the 2 arc and the 3 arcs. And the 3 is in between the 2 arcs and the 3 arcs. So now I can use proportions to solve for x and for y. So I'm going to say that 6 corresponds to 4. And that fraction is going to be equal to 8 corresponding to y plus 1. If the corresponding side lengths are proportional, then they equal the same fraction. Now I can cross multiply and solve. I'm going to do the same thing to find the value of x. So I'm going to solve this proportion on the left. I'm also going to set up 6 over 4, because those two correspond. 6 over 4, that equals x over 3. 6 over 4 equals x over 3. And 6 over 4 equals 8 over y plus 1. The side lengths are proportional. All right, we set up our proportions. Let's solve this sucker. So we're going to cross multiply. 6 times y plus 1, that equals 4 times 8. So 6y plus 6 equals 32. 6y equals 32 minus 6 is 26. Divide both sides by 6. And y equals 26 sixths is the same thing as 13 thirds, dividing each of them by 2. Y equals 13 thirds. And now let's solve for x. Cross multiply. 4 times x is 4x. 6 times 3 is 18. Divide both sides by 4. And x equals 18 fourths is 9 halves. And we have solved for x and we have solved for y. Last one for the day. Rectangle WXYZ is similar to rectangle PQRS with a scale factor of 1.5. So I'm just going to write this down so we kind of get an understanding of what this looks like. It says this one is similar to PQRS. So when I see that 2 word right there, I'm going to write that as a ratio. So it's WXYZ is similar to the PQRS. So if the scale factor is 1.5, that's the ratio of the corresponding side lengths. It's kind of like 1.5 to 1. So if the length and the width of PQRS are 10 and 4 respectively, that means the length is 10 and the width is 4. What is the length and the width of WXYZ? So if the scale factor is 1.5 to 1, the ratio of the corresponding side lengths, it should be proportional then to, if we say that what is the length and width of WXYZ, we want to know, we'll start with the length. We want to know the length of WXYZ, but we know the length of PQRS is 10. So now we can simply cross multiply here to find the length of WXYZ. So we simply cross multiply 1.5 times 10, x equals 15 meters. So it's 1.5 times bigger, 10 times 1.5 of course. We can also do the same thing with the width. If the scale factor is 1.5 to 1, we want to know what the width is. Maybe I should call this W. I should have called this L. And when I take length times 1, you just get length, right? So 1.5 is to 1 as the width is to 4 is the width of PQRS. So now we can find the width of WXYZ. You cross multiply, and 1.5 times 4, the width equals 6. 6 meters. That's why I say the scale factor is often the number that you multiply by. That's what we did here. We took 10 and 4, and we multiplied it by the scale factor of 1.5. We'll be doing more work with this when you get to class tomorrow.